series.
You're welcome.
And if that doesn't work, just pull that right over there.
Okay, well, thank you for coming tonight. I'm going to talk about my favorite subject, which is groundwater. I'm a hydrogeologist, which means I study water in the Earth system. And a hydrogeologist particularly is focused about underground water. And so that's my specialization. And I was trained at the University of Waterloo with a PhD. And I worked there as a research faculty member for 12 years before I came to Guelph in 2007. And at Waterloo and now at Guelph, I've been running a field-based research program with a large number of students and staff that helped me do this work. And so before, well, I guess I was going to say a bit about what I'm going to talk about here today. It all is summed up nicely in the word groundwater. And the institute that I created at the University of Guelph is G360. And the G stands for many things, but primarily groundwater. But in Guelph, certainly within the Grand River Basin and the Great Lakes area as well. And it's a global resource. And so we'll be talking about all those things here tonight. Given that I'm a field-based hydrogeologist, I'm involved in developing new technologies and testing them and collaborating with many folks around the globe with their ideas for new ways to monitor or measure the system that we're very interested in. And those of you that have blue ribbons on your trees in your yard, it's all about groundwater in terms of whether we should pump or how much we should pump, who should be able to pump, how much we should pay for what we pump, and all of those things. So I think it's about studying the natural system and understanding the metrics that guide those decisions. Yeah, so I wanted to give credit to my staff and students, which many of them are photographed here. I think we have photos, most of them smiling. The weather isn't always perfect, as you can see in the winter conditions. And that's what we're up to, essentially. We do quite a bit of work in Guelph and across Canada and certainly around the globe. And so I have a group right now in Sweden drilling boreholes in crystalline rock and so on. I don't do it alone. Doing field-based work on this topic is very multidisciplinary, and so I collaborate strongly with others that do similar things to me and those that do very different things. So microbiologists and chemists would fit more in the different category. I'm more of a physical hydrogeologist, and I'm trying to understand flow and transport of contaminants in the subsurface. So all of those people are part of the success. And when we're interested in managing our groundwater or water resources, we need to think about their vulnerability to various threats. And we have contaminant threats, and then we have quantity or physical threats. And often those things can be linked together. And as we grow in our population and our level of economic activity, we stress our natural environment a bit more than what we would have in the past. And those are some of the things that we're dealing with here in Guelph and certainly around the globe. I get lots of support from private sector sponsors. You can see some large multinational companies on here, the oil and gas industry, the manufacturing industry, who have sites that have become contaminated over the past decades, making products and so on. And then I'm also supported by the professional hydrogeology community. We collaborate frequently with our consultants, and there's a large number of hydrogeology consultants in Southern Ontario. It's one of probably the most densely populated area of hydrogeology experts, perhaps in the world, partly because of the University of Waterloo graduating so many scientists over the past 50 years. And we've spread across Canada and continued to develop our graduate programs and undergraduate programs at the university. That private sector money is a really valuable source of grant money in Canada, both federally as well as provincially. A lot of our engineering and science funding comes from leveraging those donations that we get from the corporate sector. And so so the private sector might be a third of my funding, and the other 2/3 would be from municipalities and these grants that I write. And so you as taxpayers have contributed to the success of our research program. And thank you, I should say. So groundwater starts at the water table and below, so it's where the pores and cracks of the rock beneath our feet are completely filled with water, or more or less filled with water and flow freely. Above the water table we have what we call the vadose zone, or the unsaturated zone, and that contains a bit of water, but it also is filled with air. So when we dig a hole in the subsurface and it fills up with water, then we've reached the water table essentially. And so groundwater is everywhere beneath our feet, all around the globe, on the continents, and it exists in these fractures in bedrock, or it exists in the pore space between the grains of sand and gravel. And if we want to access that water, we drill a hole and often put a pipe in that hole so it stays open, so we can pump that water up to surface and we can use it for whatever we need. And groundwater is constantly in motion, and it moves from what we call high hydraulic head to lower hydraulic head, and it moves from upland areas, or where the topography is higher, and discharges at surface water zones, as I'm showing here on the left-hand side. Now, so groundwater is recharged along the land surface. It percolates through the overburden, as we show here, and then it moves along these flow paths. Some are short and some are long, and that means that the residence times of the groundwater are going to vary. But ultimately, it discharges in these surface water streams or rivers or lakes as it moves toward the oceans. Now, in Canada, I would say it's primarily this condition here. In semi-arid or arid regions, we often find that surface water is perched or situated elevationally above the groundwater table, and that means that the surface water is going to recharge the groundwater zone. And so, but the main point here is surface water and groundwater are one resource. They're inextricably linked, and we understand them as essentially the terrestrial water cycle. So groundwater moves slowly compared to surface water systems that we're much more familiar with because we can see them. In sand and gravel aquifers, there's a larger volume of void space, the space between the grains of gravel and sand, and that means that the pressure that causes water to flow is going to flow more slowly. It's like a larger diameter pipe, compared to fractured rock, where the cracks in the rock are very, very small or thin. In fact, the average diameter of a human hair is about the same aperture as a fracture in the bedrock aquifer that we're seeing here in this photograph. And this is what we're standing on top of here in Guelph, and this is a view of the Dolostone aquifer that we get our water supply from. And this Dolostone aquifer underlies the sediment that forms essentially the landscape that we see, the hills and the valleys and so on. So this rock extends from Tobermory across Niagara Falls and into New York State, and essentially is underneath the sediments over in this blue banded area here. And it's known to being a very transmissive aquifer with very good quality water, or clean water. And so often the communities that overlie that portion of southern Ontario have used this groundwater for their water supply in the past, unless it's become contaminated and then they've reverted to either surface water or other options. But this is a view of the yellow area here is a view of the Grand River watershed in which we sit. And both Guelph and Cambridge are big cities that essentially pump water from this Dolostone aquifer for the water supply system. And this is a view of the aquifer as we see it in exposed sections, like in the Dolime Quarry, where we can get a good view of the rock, or other quarries that we have around Guelph that show us this bedrock. And it gives us a view of the nature of the fracture network. And the fractures are allowing the water to move the most freely in the system. So you can see the location of our University of Guelph campus, and all the yellow locations are places where we're doing research in the city. And you can see we've got more than a dozen locations, and we're also working in the neighboring townships. So we have lots of data that we're collecting in and around this region to understand the flow system as well as this aquifer in particular. And it's from the field data and the measurements that we make in our boreholes and our multi-level systems for monitoring this groundwater that we've developed this cartoon view of the rock and essentially illustrating some of the characteristic or important features of this aquifer. So the darker brown on the top is our overburdened sediments. The glaciers came by about more than 20,000 years ago and laid down these sediments, maybe carved some erosional features into the top of rock, what we call bedrock valleys. And so this is what we see at land surface. And underneath that sediment, we have this stolistone aquifer. And we have different aged rock formations because it takes perhaps hundreds of thousands of years to form this rock. And so that's the combination of rocks that we have beneath our feet that we drill our boreholes into or our water supply wells into and pump water from those long open pipes essentially. So they act like straws into the subsurface. And so the groundwater that's moving through the system is perhaps being pumped in this well and coming to surface. And what we know about this bedrock is it has different zones of varying transmissivity or permeability. And so the rate of flow may be different at different layers. Now this feature in the middle here is what we call an aquitard, a lower permeability layer. And those are very important features in this aquifer and everywhere in studying groundwater because they slow down the rate of groundwater movement. And that means that groundwater is going to spend a lot more time getting from the recharge area to the discharge area, which might be this well. And that means there's more time for attenuation of the chemistry and improving the water quality because the subsurface is this great filter and has the potential to improve our water quality that comes to us from the surface and as it moves through that subsurface over perhaps not just a few years but perhaps decades or maybe even thousands of years. So one of my first research sites in Guelph is located in the northwest quadrant at Guelph Tool. Guelph Tool was a sponsor of my research at one stage, and their issue was an industrial contaminant that I know very well. But the two wells here that I'm showing in the well field, the City of Guelph well field, the Saco and the Smallfield wells, had been shut down in 1994 because of trace amounts of this hydrocarbon contamination called trichloroethylene. And so I brought my students out there and we got to work trying to study the system. But as you know, almost all human activities leads to some type of contamination or waste, and so there are a variety of potential threats, contaminant threats that we're dealing with. So what you see here is a cartoon view of the subsurface. You can see our water supply wells as pipes into the subsurface that are pumping and bringing water up to these water towers. We have a few of them, I think there are 3 of them across Guelph, that store that water before it's sent to the treatment, before distribution into all these homes and industrial properties and so on. Now wastewater gets collected from our homes and goes into a sewer pipe that runs underground, and that contains perhaps some contaminants of different types, whether it's black water from our toilets or whether it's gray water from our showers and so on. It might have soap and different issues that we have to deal with. So it's meant to be contained, but sometimes it leaks. We also have agricultural type operations around the landscape. They're using fertilizers and pesticides, and not all of that gets taken up by the plants. So some of it gets recharged into our groundwater system and so on. So these are the variety of threats that any community, a thriving community in particular, is going to be dealing with in terms of their water cycle. So we have a natural water cycle, and then we have a human or community water cycle, and they aren't the same. One taps into the other, uses that water temporarily, and puts it back into the natural system somehow or somewhere, usually in a changed state. We definitely change the temperature, we often change the chemistry. So those are the issues that we're dealing with in terms of the water cycles that pertain to Guelph and even small households in rural areas as well. So one of the main questions here is, how fast does groundwater move through the system? And then depending on the flow rate, what type of reactions might be interacting with that groundwater to change its chemistry as it moves. And in a fractured rock aquifer, we've got velocities of about 1 to tens of meters per day. So that's pretty fast, but not as fast as a river. So I mentioned Guelph Tool, and most commercial industrial activities have used hydrocarbons, either what we know as gasoline when we fill up our cars, or a variety of commercial activities that I've shown here at the bottom. Dry cleaners use these chemicals, machine shops, automotive repair shops, and so on. So there's a lot of different operations within a city or a small town that are going to use these chemicals. There's some that float on the water table, and there's those that sink because of their physical properties. They're denser than water. Both are not completely miscible with water, so they tend to exist in the subsurface as an oily phase, just like the oil and vinegar situation. So two fluid phases sitting in the subsurface. Now in bedrock, which is what we're mostly dealing with, I'm going to focus on the dense non-aqueous phase liquids, or what TCE represents is a common example of that. And when it's released, it's going to migrate deep into the subsurface, and it's going to find its way into the cracks in the bedrock, because those are the paths of least resistance to flow, right? That's what groundwater is moving preferentially in, and that's what these oily liquids like to move through. And conceptually, when we have a release, and oftentimes these releases are perhaps not much more than a 55-gallon drum, or perhaps hundreds of gallons released at any particular time by mistake. Anyway, we create a zone in the subsurface where the oily phase sits and kind of becomes stationary. And what that means, though, is as groundwater is always moving, it can move through that zone, dissolve a bit of that contaminant into the water, and keep moving. And that's what we call a plume, a groundwater plume. Very similar to the air plumes that we see from a smokestack. So that's, I think, where we borrowed the term from. So this is the groundwater plume here, and we're interested in how fast this plume is going to move, because it may not move anywhere near as fast as the groundwater's moving. And that's because of a variety of processes that can operate on that plume. So this happens to be the plume at the Guelph Tool site. And there are lots of industrial properties adjacent to each other, but we were looking at the TCE contamination at a snapshot in time. So this is a map view of trichloroethylene in 2008 on the left-hand side. And the black dots essentially represent all the wells that we have in the subsurface, and that allows us to contour or draw this map of the concentrations above a certain level. And then we went back 5 years later and mapped the same plume in detail, and we saw that instead of getting bigger, which is what it should be doing if the groundwater keeps moving in the same direction and there are no degradation reactions going on, we saw that it was smaller. And we saw that inside the limits of the plume, it was even decreasing concentrations. And when we looked for the degradation products, we saw them as well. And there are lots of diagnostic tools that we use to quantify how much degradation's been going on and so on. And so after 30 years or 40 years of contamination, the aquifer and perhaps the chemistry and the microbes in the aquifer acclimated and started to work away on this contaminant. And we start to see what we call attenuation. So these processes, some of them are physical processes like diffusion and sorption and dispersion, and then some of them are chemical and microbial reactions that destroy those chemicals, turn the trichloroethylene into something like CO2 and water, or methane or ethane, which is a dissolved gas in water. And so we essentially reduce that contaminant mass, but over a long period of time. The bigger the spill, the longer it's going to take, likely, to clean these sites up. So that's an industrial commercial type of contaminant. It's just an example of several chemicals that can be found locally in our groundwater system. The good news is we see evidence that the subsurface might be able to attenuate or assimilate those chemicals over these longer periods of time. Another class of contaminants come from our septics and our sewer systems, and might even be derived from landfills. And then we have to be careful about road salt and what it might be contributing to our groundwater quality. So here we see that septic systems, which essentially receive waste into a tank, and it's purposely anaerobic at that stage, but then it's discharged from that tank where a bit of degradation is expected to occur out into this leach field. And in the leach field, it's meant to be aerobic, and it's purposely turning the organic nitrogen into nitrate. And we all know nitrate is a regulated constituent in our water. We have a regulatory limit. So we actually purposefully design our systems to contaminate groundwater, but we're expecting the subsurface to ameliorate that nitrate with time and distance. Right. And the same thing is true with solid waste landfills, right? They're meant to be underground storage with the expectation that microbes and chemical reactions will help to degrade that solid waste over time. And the question is how long and how far might leachate get into the groundwater system? And we hope to manage those plumes away from our well fields that we're using for drinking water supply. Another really important and big source of contaminants would be agriculture, especially what we call industrial agriculture, right? So for the last 50 years or so, we've been pumping what we call chemical fertilizers onto the land and pesticides to improve our crop yields. And I suppose even the look of our food that we eat. But agriculture isn't just for food, it's also for energy, and we're using it for products as well. So when we're growing these crops and livestock and so on, we need to think about the full suite of things that are being raised. So we're going to go to the southeast quadrant now of Guelph, and we're going to look at a corridor of activities here. You can see that we've got the Arkell Research Station here, which is where we're doing lots of research on plant and animal research, and we've got the golf courses along Victoria Road. And so we've been able to partner with these landowners and get access to drill our wells and collect data in our specially designed fashion to gain some insight of what's going on. In particular, we're looking at high levels of nitrate that have been appearing in one of our water supply wells in the city called the Carter Wells. And I didn't provide a plot, but at some time in the past 20 years or so, there were concentrations of nitrate elevated above the drinking water limit, and so the city was quite concerned about whether that projection of concentration of nitrate was going to continue to grow, or what. And so what I bring to the table are some tools that go down these boreholes, and we use multilevels that allow us to get samples and measurements at multiple depths. And so this is just to train your eye, I suppose, to think about things in a vertical profile. And I call them high-resolution multi-level samples because I like to maximize the number of data points that I get. Now, that means I'm pushing things to an extreme, I suppose, because I'm trying to open up the black box and learn things in a bit more detail that others haven't tried to learn before. And the data that I collect is going to be information about the hydraulic head and how that varies in the subsurface, because that gives me insights as to where these aquitard layers exist, and then concentrations of different chemical constituents. And they may be naturally occurring chemical constituents like sulfate, and nitrate can even be naturally occurring, or it could be isotopes of water, or it might be these contaminants that I'm interested in. And so out there at the Arkell Research Station, one of our high-resolution multi-level systems, which is shown here as it was designed and built in the subsurface, and you can see that my ports are the white spaces between each of the packers, which are black, and they're sealing, each of the ports are sealed with these packers. So we got 25 or so of these ports. over about 100-meter distance or 75-meter distance, which is the typical thickness of our aquifer here in Guelph. And then I've got a measurement of hydraulic head, so I can see that I've got high pressure, shallow in the subsurface, and then I lose that pressure through this zone of the subsurface, which means I've got some type of impedance layer. And then I've got lower heads with depth, and that tells me about the layers of my aquifers. And then I can look at the chemistry. So I'm looking at tritium as a tracer. Tritium falls out of the air in the rain that falls to the surface. It's naturally occurring at low levels. And so we use it as a groundwater tracer, and it tells us about the age of the groundwater, because once it hits the water table, it starts to lose that signature. And so shallow, I've got very high levels of tritium. That's relative to the input concentration. They're not high levels in terms of any danger. Very low levels in my aquitard, which is thought to be low permeability, and this kind of reinforces that. And then I've got a little bit higher levels down here. And one of the things that might come from this is, first of all, more confidence in the aquitard and how long it takes groundwater to move from shallow to deep in the system. But also it might give me some evidence that there might be something that's breaching this aquitard, helping to facilitate some water to get deeper faster than perhaps it otherwise would in a natural situation. So far we've talked about chemicals or contaminants that are dissolved in the water phase, and so they're susceptible to these processes like diffusion and dispersion, and they help to attenuate the concentrations strongly. But particles like viruses or perhaps nanoparticles or things like that are they may not be susceptible to those processes. And so we do get concerned about them in another way, in that they may travel much faster than the road salt or the other contaminants that we're more accustomed to looking at. And so that brings us back to this question about the rate that groundwater is moving. It's very difficult to measure that directly, so we usually infer that based on the tracers of the system, like the tritium that I was just talking about. But that doesn't help us when we're concerned about a particle like a virus or an E. coli, right? These microbes can move through the cracks in the rock as well. I started working on this topic of virus and groundwater back in 2001, and I worked with Mark Borchardt from Wisconsin. He now works for the U.S. Department of Agriculture, but he's a virologist, and he was studying virus occurrence in Wisconsin groundwater, and I was working with colleagues in Wisconsin at the time, and so we were particularly interested in how fast these viruses might move in groundwater, especially bedrock. So I think the last slide showed that, or made a comment that these viruses typically have a finite lifespan, or they're not really alive, but we can call them an active span or period of time, which is generally thought to be 2 years. But they survive longer in colder climates. So Canada's more vulnerable to virus longevity than perhaps southern California or Florida. Anyway, this paper just came out. My student Amy Allen graduated a couple of years ago. So what we did is we selected 22 locations across southern Wellington County, from center Wellington down to Puslinch or Aberfoyle, and we selected a variety of well construction types. So we've got big municipal supply wells. We didn't use any in the city of Guelph, so the results don't pertain to the water supply wells at Guelph. But we did use some of the city of Guelph's monitoring wells. And then we also have private wells. Private wells tend to be shorter or not penetrate as deep in the system. And so the conclusions are shown here. This is a map of the townships. You can see the distribution of the wells here with these colored dots. And essentially, Amy's indicated which of the virus types were detected or measured. We sampled 6 consecutive months, one sampling each month, and that meant we had 6 samples for each well. And then what we found is almost half, or 10 out of the 22 wells that we sampled, at least one of those 6 sampling rounds had a positive detect for viruses. And that's consistent with the findings that Mark Borchardt and his colleagues are are getting in many other studies. Viruses come and go very quickly, so temporal or multiple sampling events are required to actually see the vulnerability of a well to virus-type contamination. So viruses are getting into our groundwater from our septics or our sewers, right, because it's from human waste, or perhaps animal feedlots and so on, because there are animal viruses as well. But in those waste streams, we also have things like artificial sweeteners and pharmaceuticals. We also have personal care products that are of concern. And so our waste streams are getting much, much more complicated or sophisticated than what they used to be more than 50 years ago. So if we're thinking about the past 150 years since we've settled in this area, we've really changed the way society functions and especially how we rely on our groundwater water sources to support our daily activities. So in summary, we've got different types of contaminants that have the ability to travel deeper and farther, faster versus shorter and not so far. The amelioration or assimilative capacity is going to vary for each of the different contaminants, and that's something that we currently don't factor into our source water protection legislation and operations at this stage. But those are things that I think we can readily move to and should move to as we think about more sophisticated management strategies, or perhaps how my research might inform some of our activities. So this slide just shows a groundwater flow system in cross-section. It shows different layers of soil or rock with the blue zones representing the higher permeability zones, and then we have the brown zones that represent these aquitars, or what we call confining layers. And so you can see that depending on the position along the water table that water gets into the subsurface, it might fall along a very long flow path that goes deep into the subsurface that might take thousands of years to make it to the discharge zone. Or you might fall onto a short flow path that goes reasonably quickly. Maybe this only takes a couple of years to get this far. So that is going to matter in terms of the residence time and perhaps the time for reactions to occur. So I already mentioned multi-level monitoring with those vertical profiles that we've already had a look at. And we can do that with what we call conventional monitoring wells, which are individual pipes that are drilled into the subsurface and have an open section at different depths that we choose to select. We can put all those pipes in a single borehole, but that hole would have to become a bigger hole. Or we can choose to use a variety of commercially available multi-level systems that have been used since the late 1970s. So there's 4 different vendors of commercially available systems, and we're using all of them. They all have different, each of these systems have their advantages and different disadvantages, I suppose, given different hydrologic conditions or types of data that we'd like to collect. So we pick and choose from them, I suppose, strategically. And then we're designing our own because we've thought about these systems a lot, and we see opportunities to make them function better for the purposes and perhaps even be cheaper. And our goal or our hope is that multi-level monitoring would become more standard as it's not used to its full potential. But we've been collaborating with the City of Guelph since 2006, designing and installing multi-levels in their regional monitoring network. The Tier 3 studies that have been promoted by the Source Water Protection Act have allowed the City of Guelph to modernize their monitoring network so they have a good sense of the water balance as well as the chemistry of their water throughout their capture zones. So we've seen this already, and I guess essentially I'm punctuating the fact that we've been working with the city, and the city's kind of advanced their understanding of the subsurface flow paths based on that advanced monitoring network. But I mentioned, in addition to chemical threats, there are physical threats. And what could they be? So some of them are as simple as how we design our wells and whether or not we keep them as long open screen intervals from top to bottom, perhaps puncturing through this aquitard and creating a short circuit or a conduit or preferential pathway, right? So that 2-inch or 8-inch or 12-inch diameter hole for our water supply well is going to allow water to move down through that aquitard much more quickly than it would naturally on its own. Or it could be the presence of these quarries that we're digging down deep into the rock. The Dolime quarry is a prime example, and it's essentially mining the rock that forms our aquifer. So, but I suppose most contentiously, it's whether or not they should stop before this important aquitard or not, or whether or not this breach is going to perhaps make some of the existing water supply wells a bit more vulnerable. Anyway, you've probably read about that in the news, and that's certainly an important topic, hopefully with some scientific input. And I think it has been, but I'm sure there's still lots of questions that we could try to better answer. So this is the position of the Dolime quarry. As you can see, it's proximal to a number of our water supply wells. And we're engaged in some sentry monitoring work right now. And what that means essentially is we're putting a more robust monitoring network around some of these active water supply wells to better understand the chemistry of the water coming near it. And here's a view of the quarry as it stands, probably almost 10 years ago now when I was in there. And I mentioned water supply wells that might be fully screened throughout the entire length of the bedrock. And we've got technology that we've been using in testing to seal those boreholes on a temporary basis. So it's expensive to close out or abandon a well, especially if you think you might have a future use for it. But it could be advantageous to seal it so that water doesn't preferentially flow in from the shallow zone that might have some road salt or contamination in it and move down deeper into the aquifer and perhaps contaminate the deeper water quality. So this Tier 3 monitoring network has also given us information about tritium, and tritium being this water tracer, it tells us the relative age of the water in the subsurface, and we see the bigger the bubbles, the younger the water. And so we see that there's quite a bit of variability across this system. And so that's helpful for us in terms of understanding the flow system. So we have different ages of groundwater shown here, as we talked about already. And our hope is the deeper the flow lines go and the deeper our aquifers, the more confined or protected they are, perhaps the much cleaner or pristine those water sources might be. But what we find, at least across Canada, where our groundwater resources are generally shallow, most of our fresh water is shallower than 150 or 200 meters deep. We often see that there's traces or certainly evidence of young groundwater mixed with our pumped water at surface. So that may have to do with how our wells are completed, or perhaps the 7 or so decades of industrial and agricultural activity that has impacted that water. We read a lot in the New York Times and elsewhere about the global water crisis, and I suppose we start to think about how that pertains to us here locally. And yet I think there's lots of variability around the globe here in terms of the amount of rainfall and the amount of recharge that gets into our groundwater system and what type of threats we're dealing with the most. I would say that here in Guelph, our big threats are more the contaminant or the water quality issues, not the water quantity issues, which are getting a lot of attention right now in terms of pumping or permits to take water. But that doesn't mean that's not an important issue, and in fact, it's intertwined. Just some perspective, groundwater makes up 96% of the available fresh water around the globe. So we remove the ice caps or the frozen water from our calculation here because nobody accesses that for drinking water. And so the bulk of our water is in storage in the ground beneath our feet. And so when we talk about a water crisis, we're talking about a groundwater crisis. And groundwater and surface water are linked. 50% of the world relies on groundwater directly for their drinking water. And some of them are major cities with tens of millions of people. And so there's a lot of pumping of groundwater happening in those places. And associated problems come with that, like subsidence, right? That's another topic in another day. So many people live in arid regions or dry regions around the globe as well, disproportionately, but there's still groundwater in those deserts, which is surprising to people because there isn't any surface water. And so if we think about solutions for some of the population centers around the globe, perhaps it's better technology for those regions or climate zones to access the water that's underneath their feet. And then they're going to need to know what their sustainable yields could be to maintain that over the longer haul. An example is the Gobi Desert in China. And you can see a hand-dug well in this photograph that shows that the water table is not very deep below the land surface, offering a source of drinking water for the folks that are living there temporarily. But the bigger issue, the one that we're dealing with here in Guelph, or certainly in Ontario with the moratorium on bottled water, is about the fear of pumping too much. And certainly there's lots of news about pumping too much in Saudi Arabia or California and so on. And when and how that occurs is a matter of water management and policies that go with that. So when you pump groundwater, you lower the pressure in the well, or you lower the water level in an open pipe. And we call that drawdown a cone of depression. So you can picture it here. I've sketched it out for you, right? And so this is what we call the cone of depression. And the water that's been taken out of storage in the system, you can imagine, is that area created by that cone of depression. And if we have multiple wells like we do in the city, we're going to have multiple cones of depression. And that can exacerbate the rate of water level decline when those cones of depression overlap, right? And so that's the fear, I guess, that we're thinking about here, is whether or not we're going to be overdrafting and drawing our water table deep into the subsurface, which means the discharge to our surface waters will decline. Or the cost of pumping that water in the future is going to go up because it costs more to pump from deeper depths. And that's what's happening in California. All right, so the North China Plain is another example where there's many people live in that region near Beijing. They're producing a lot of agricultural products, and they're overdrafting their aquifer. And so they have recorded the largest drawdown cones anywhere in the world. And the thing is, as groundwater moves slowly, the time to naturally recharge that depleted groundwater reservoir could be hundreds of years or longer, even though it was depleted perhaps in a matter of tens of years. And so here's the plot that was obtained from a colleague showing the depth of the groundwater. Used to be at about 3 meters below ground surface, and now, or after they'd pumped very hard, essentially it's more than 15 meters below the land surface. I mentioned California. It's showing up in our scientific literature. This is where the bulk of our agricultural products, our produce and our dairy and fruits and vegetables are being grown, is in California. And essentially, they've grown those vegetables by mining the groundwater. So they've lowered the water table by tens and tens of feet or meters. And so it's now at a serious level in the sense that wells are drying up, and they're also dealing with a drought at the same time. And so there's multiplicative issues coming to the table. But those are quite different than the situation here in Guelph. So we have a distribution of fresh water, and most of this is groundwater shown here on this plot. And it's variable around the globe. And we happen to be in more of a water-rich part of the world, and certainly our population density is quite low as well. Only about 30% on average of the population rely directly on groundwater. The rest of us rely on surface water for our water supply. Mostly the rural areas are directly dependent on groundwater, but communities like Guelph and Cambridge, Elora, Fergus, and so on are still groundwater dependent and expect or want to remain so. If I look at the Grand River watershed, the upper half of the Grand River watershed are communities that are all reliant on groundwater, and most of them are reliant on bedrock, the Seine Dolostone aquifer here. So here's our population, and these are our neighboring towns that are all sharing this same aquifer. And so one of the things that's talked about is our cones of depression and whether or not they're interfering with one another. And the issue here is when you live in the same watershed and you're essentially sharing this resource, and some of the communities are upstream and some of them are downstream. And so to be mindful, I suppose, of our resource, we need to also be mindful outside of our community boundaries to be protective of the resource. I made a comment about the two cycles, the natural cycle and the community cycle. I'm participating in a conference on Friday with the First Nations people at the university, and this is something that's very important to those communities as well. And this shows the water balance. This is a complicated slide. It's just meant to impress you, I suppose, of all the different boxes that deal with water in one way or another. The gray shaded area is the supply side, and then it gets distributed throughout the community and gets used and then collected back as wastewater for the most part, but not all of it. And we need to understand the system. Here we've got a variety of uses, and I think the most important one to see here is the City of Guelph extraction is by far the biggest use. We've got industrial users, we've got golf courses, we've got Sleeman's use here as, I guess, a comparison for Nestle's use down here. And you can see we even have leaks in our water mains that lead to more use of our water, I suppose, than many of these smaller uses to put it in perspective, I guess, in terms of the situation that we need to manage. Exporting water, whether it's in bottled water or the juices or beer or wine and so on, they're all essentially what we call virtual water. All the livestock, all the grains that we grow and so on, they tend to be exported out of our watershed as well. And this term virtual water is a very important term because, in fact, we've started to appreciate why wars aren't being fought over water in the Middle East, for instance. And that's because places like Israel are getting their food from places like Canada and the US and so on. And that's really helped to ease that burden, I suppose, in terms of the distribution. Yep.
Can you go back to the previous slide?
This one?
Yes.
Yep.
So the two things at the bottom are what what people are talking about for Nestle.
Yep.
Where's the gravel pit and their extraction in there?
That's a good question. It's probably lumped into the industrial water uses because I think we would have probably put the mining in that category. So it's at the bar right there.
And that's just the gravel, that'd be the dolomite pit, or all the gravel in Center Line?
Well, this is the City of Guelph area, so we would have included nearby gravel pits, Aberfoyle, and the Dolime Quarry, but not farther out than that. But there's several of them around the area. I'd have to check on the numbers, and certainly we've used the source water protection reports to gather these up and put these numbers together in this graph. So we can follow up with you if you have more questions on that. Yep.
And so the Nestle's, it looks like their permitting is sort of twice again what
they have a permit to take twice as much as they actually extract. Yep. And there are other bottled water operators within southern Wellington County as well. Nestle's not the only one. But this whole concept of virtual water, I think, is a very important one when we talk about imports and exports and so on. And This issue that we've been dealing with in the last 8 months or so, with a moratorium on new permits to take water or testing for bottled water takers and so on, I think it's certainly brought a lot of attention to the water issues, which has been good for us. But I think the issue is much, much bigger than what's being talked about and being dealt with here. And certainly this isn't the biggest threat that we're dealing with by far. So in a way, it's a red herring. But if we can capitalize on it for the good of what it's doing, which is bringing attention to our water resource issues, then I think that's a positive thing. So here's an upcoming event. The Wellington Water Watchers and others are advertising this on June 11th. And I was really struck by the graphic. I think it's a beautiful poster. And the issue here looks like we're at a crossroads in thinking about water for life versus water for profit or not for profit. And it confuses me, I suppose, or causes me to think hard on this, because we use water in so many ways within our community for profit. We can't have a viable community without economic activity. So I've tried to kind of show examples of that through this evening, and I guess I hope that that's giving you some pause to think about the issues and how complicated they are. They're important issues, and we need to do our best to do a scientifically informed job. So, and other people are speaking up on this as well. I think whether it's a local issue and it's getting lots of attention here in Ontario, which is well deserved, but I think needs to be much broader and much more integrated into the complexity. These are just quotes that I've taken here. This is much more of a global comment about water and how important it is for us to gather data and way more sophisticated data than we have been collecting, even through our Tier 3 studies, to answer the nature of the problems that we're going to be forced to deal with. And with that, I'd just like to leave you with my concluding remarks, which I've listed here. I think Canada is going to realize that even though we feel there's lots of pressure for exporting our water, it's only going to get worse in future decades, because we're a water-rich country, especially compared to our per capita. And how we make decisions in managing that water and so on, I think will be really important for us as well as the world. If we're not willing to export water in its virtual forms, in its many ways that it can be exported, we're probably going to have to deal with a lot more immigration, right? Because of population distribution. But we have technology, and we can start applying those technologies, I think, to better inform our decision making. And I think that's really where I would like to leave us, because I think that's what has been stirred up in the last year or so and is actively happening in our community as well as in Ontario. And so I'm excited about that challenge. So thank you.